In Unit 10, we're introducing logarithmic functions. Logarithmic functions are the inverse of exponential functions. What that's going to allow us to do, it's going to allow us to algebraically solve things that we could only graphically solve in the last unit. When we saw any kind of exponential equation, especially in all those application problems, and you were forced to make those graphs and plot the horizontal line and find the intersection point. That was the only way you knew how to solve those at that point. You could guess at numbers, but you could be guessing a long time if I asked you to come up with x to any degree of precision. So now in this unit we're going to learn how we can solve these exponential equations, and we're doing it by discovering what their inverses are. Let's take a look at a picture first. Got this exponential equation or exponential function for the x. If I look at the domain of this, I know the domain is all reals. It goes all the way to negative infinity on the left, and it will continue moving to the right very slowly, but moving to the right forever. And the range, this does not exist in quadrant 3 or quadrant 4, which means it never comes below 0. As a matter of fact, it never actually touches 0. So the range of this exponential function is y is greater than 0. And we saw that with all of our exponential growth and exponential decay functions, as long as we hadn't done any shifting around the graph. Okay, let's take a look at a calculator picture of not only that blue exponential function, but the black inverse function. You can see that it's a perfect reflection. The blue and the black are perfect reflections over that line y equals x, and that's how we can tell an inverse. If we do have a perfect reflection over that red diagonal line y equals x, we know we got inverse functions. We've seen that already. So take a look at what the calculator has plotted here. The calculator has plotted f of x equals 4 to the x, and it's plotted this other function, and inside this other function you will see the abbreviation log, log. It's an abbreviation for a logarithmic function, just as sin is an abbreviation for sine, or tan is an abbreviation for tangent. So we can convince ourselves that we in fact do have an inverse by looking at a picture of the graph. The domain, if we look at this black function, well, we know that when we take inverse functions, the domain and the range switch around. Whereas before we had the domain for the blue function all reals and the range y is greater than 0. Take a look at what happened to your new black logarithmic function. The domain now is x is greater than 0. Because you do have another asymptote here. It's going to come infinitely close to x but never touch it, and it's going to go forever to the right. That's obvious. The range is now all reals. It's pretty obvious that this is going to continue on down forever, and even though it moves up ever so slightly, it will be moving up forever as well. So the domain and the range have also switched places. Okay, so why do we want to use these logarithmic functions? Because it gives us an opportunity to solve these exponential equations. Well, when we had an equation like this, that wasn't so tough. We could solve that simply by coming up with the same base. We left 2 to the x the way it was, and we changed 8 instead to 2 to the third. And as soon as we had the same base, we could set those exponents equal to each other. So I had x equals 3, and I had solved this one. Well, that's great when you've got something where you can come up with common bases, but when you move on down to this next equation, 3 to the x, and now we've got to try to figure out some exponent here. And we don't know what the exponent is. We could start guessing at it. I know that 3 squared is going to give me 9. I know that 3 cubed is going to give me 27. That means I need a number that's bigger than cube. I'm going to need 3 point something. If I go all the way up to 4, it's too big. Now I'm at 81. So 3 cubed would give me 27. 3 to the 4th will give me 81. I know that this exponent has to be somewhere in between 3 and 4, but again, I could spend a lot of time guessing at it. So let's look at how we can use the logarithmic functions to answer the question for us. Okay, it's important to identify the parts of this log equation. We'll start with the word log, again short for logarithm, and you'll find a calculator button with the word log on it that you'll be able to use. This little b down here is a subscript. It's not as big as everything else. You can see that it actually looks smaller. Much the same way when you write an exponent, it is not as big as everything. It's not as big as everything else. It's a smaller number. The font is smaller, and it's up higher. Well, this is a base, so it's a smaller font, and it's actually lower. So this is the log base b of a is equal to e. All right, and that's so those are the different parts of the log. And I'm actually going to change this A to a Y to be consistent with your notes packet. The log base B of Y is equal to E. Now, a handy way to remember how that lays out there, I just say log by. If you say log by and you spell out the word BYE, that puts everything in the right position for you. So log base B of Y is equal to E. Tells us where everything goes. That A, or that Y as it is, I'm putting it in position, is called the argument of the log function. It's also known as the power. Remember, anytime you have a function, like when we had sine of 25 degrees, well, that's an argument of the function. It's really an input to the function. So if I'm going to be using a log function and it's base B, then Y is going to be the input to that log function. So I call that the argument of the log function. It's also called the power. How does that help us solve the exponential equations? Well, let's take a look at this relationship here. If I have an exponential relationship in the form that you see on top, I can convert it just by moving everything to the proper location to the log equation on the bottom. So that's what we'll do. We'll go back and forth between this exponential equation and the logarithmic equation. A base to an exponent is equal to the power y. The log of that same base of that power y is equal to the exponent. And another thing you can think of is that the exponent goes at the end. The b is the base. If you can remember, the b is the base and the exponent goes at the end. There's only one other place left for that power to go, and that's the argument of the log. So again, practice going back and forth from one to the other is what we'll be doing today. On the left, we have the base to the exponent equals the power. On the right, we see that the log of the power is the exponent, and we have to use the same base on both sides. So an exponential form and a logarithmic form, back and forth depending on which one you need. Also, depending on what the instructions are asking you for, pay careful attention to the instruction in this unit so you'll know exactly what you're supposed to do with these. Let's look at some examples. And I've got these two on top of the sheet for reference for you, or on top of the slide here for reference, but you won't have those when you take your test or when you take your Regents exam. You'll have to remember how to exchange the two. So we start with a request to write the inverse of f of x. Okay, so we're going to write the inverse function. Remember that minus 1 means the inverse of this function. F of x is equal to 3 to the x. Well, before when we wrote inverse functions, we swapped x's and y's. We're essentially going to do the same thing here. Instead of f of x, I'm going to write y equals 3 to the x. And to take an inverse, I'll swap positions. X becomes y, and y becomes x. Now this is really an inverse, but I'm kind of stuck here. The way that I am going to solve this is an inverse equation, but in order for me to write it as a function, I'm going to need to get that y inverse by itself. Let's look at the next one down here. I need the inverse of this function. Well, this one says y equals log base 8, I believe that is, of x. And now if I want the inverse, I'm going to switch y to x. I'm going to switch x to y. That's really a y inverse. And in order for me to come up with an inverse function, I'm going to have to get that y inverse by itself. I'm going to have to get that y inverse by itself. That's where going back and forth from one version to the other is going to come in handy for us. For today, we're going to leave those as is. Tomorrow we'll learn properties of logs, and that'll help us get that y inverse by itself. That'll allow us to write it in a proper function form. Okay, so let's practice going back and forth. We have to write the following exponential equations in logarithmic form, so we will just be moving position. Logarithmic form, I'll start off with the word log. The base in this problem is an 8, so I'm going to put a little 8 down here below the line. The exponent always goes at the end, and that's a 2. And the 64 is the power, which also, oops, that's not a 4, that's a 64. Power, which becomes the argument of the log there. So we'll put that in there. And so you have two statements that mean the same thing. On this side, I'm going to begin with the word log, if I'm putting it in logarithmic form. The base in this problem is a 2. See that there? We'll leave space for the argument. The exponent goes at the end. This exponent is a -1, and then the power is what I have left for my answer. That's the, oops, that's a 1/2. So we're just going back and forth from one form to the other, exponential to logarithmic form. Now we'll do the reverse. We'll take a logarithmic form and put it into exponential form. This isn't hard to do. The base is 3. The exponent was at the end. That's a 4. And the power is equal to 81. That's the argument of the log. And you will often see these written without parentheses. I don't care for it when it's written without parentheses because I think that makes it more obvious where your argument is. When you try to use these in your calculator, just like the trig functions, is immediately going to open up parentheses because it needs an argument of that function in order to work properly. On this side of the equation, we've got log base 4 of the power 32 is equal to 5/2. So we'll use a base of 4, we'll use an exponent of 5/2, and that answer would be 32. And you can convince yourself that that's true with what you know about fractional exponents. Okay, we're going to do some evaluation. We've got this expression, log base 5 of 1/25. And I had showed you that yesterday. You wouldn't have any idea what to do with it. Well, we really don't know what it equals. So let's say it equals x. Same thing here. We don't know what it equals yet. So let's say it equals x. And now let's turn this around, turn it into our exponential form. Our base is 5. Our exponent is x. And the answer is the power 1/25. Over here, this is 2 times, that's a coefficient of 2. It's got nothing to do with the log itself except that I'm going to evaluate what's inside those blue brackets and then multiply by 2. So before I can start switching things around in here, I'm going to divide that 2 out on both sides. This will leave me with log base 4 of 1/16 is equal to x over 2. My base in this problem is a 4. My exponent at the end is an x over 2. And my power, or my answer here, is 1/16. Okay, what do you know about fractional exponents when you see them? You know you can refer to fractional exponents by raising both sides to the same power. I'm going to raise both sides to the 2/1 here. Move my little recorder out of the way there. And let's keep going. These 2's are going to cancel out. That leaves me with 4 to the x is equal to, well, I'm squaring a 1 on top. That's a 1. On the bottom, I'm squaring the 16. So that's going to be 16 squared. Or it's going to be 4 to the x is equal to 16 to the minus 2, just using your negative exponents, which is going to be 4 to the x is equal to, I'm going to replace a 16 with a 4 squared. Oops, that didn't work out so well. Let's try that again. 4 squared. And the minus 2 is still outside of the exponent there. Now I've got same base. I can set those exponents equal. That's going to tell me that x is equal to -4. So a little bit more work there. You're working with your exponents, but still reaching the answer. Okay, so that's what my answer. Oh, I didn't finish that first one back here. So let's change that 1/25. Let's turn that into 5 to the minus 2. This is 5 to the x, and in this one the answer is x is -2. So you didn't see this as a solution, but you could say, well, since it's algebra, I don't know what it is, we'll call it x, and we'll solve for x, and that'll give me the value. The value of that is -2, the value of this one's -4. We can move the x into a different part of the problem, and we'll still apply the same principles in order to solve it. We'll turn it into something we can recognize as an exponential form. So we'll use a base of 2. We'll use an exponent of 4, and the answer is the power, which is the argument of the log. 2 to the 4 is equal to x. That tells us that x is equal to 16, so we just solve for x. And on this one over here, let me buy some space. And that's a log base b of 27 is equal to 3. So we'll put a base of b, an exponent of 3, exponent was at the end, and that is equal to the power. Which is 27. And we can take a base of 3 when we have variables in the base. We can raise both sides to the 1/3 power. Some of you may see, might have recognized what it was, but this is the proper way to solve. And I get 27 to the 1/3, which is the same as cube root of 27, which is the same root as 3. same thing as 3. You will have some tonight on your homework sheet where you're going to be given a couple of expressions combined. You might be given log base 5 of 1 over 25 plus 2 times log base 4 of 1/16th, and all that means is you'll have to evaluate the one side, you'll evaluate the other side, and when you finally get two numbers, you'll add them together. Or you might have 3 parts or 4 parts to it.